So just confirm again with this example. We have a concrete section 16 by 30 inches. Effective depth is going to be 27. It's going to be 30 inches subtracting the 3 inches. Concrete is 3,000 psi. The steel is 60 ksi yield strength. And I have 2 number 8 plus 1 number 9 at the bottom as reinforcing. And the question is, we need to check the minimum flexure steel ratio. Flexure means like for bending. I'm going to go back here one slide, just confirm what we have read in this slide. Minimum reinforcement for bending, for beams, and it's going to be only for beams. For example, in footings and in concrete slabs, they're going to be also exposed to bending. But these two equations won't apply to them. So this is going to be only in beams. You see this? So be sure that you remember, this is going to be only in beams. We have two equations for two minimums. Usually when you have two minimums, you're going to be taking the larger of the two and use it in your analysis. The first equation here includes the concrete strength. So if I see here 3,000 psi concrete in this equation, what you're going to put here under the square root is going to be 3,000, not 3 psi. If you remember, this is a psi code. Same thing for this F sub y. It's going to be 60,000. Now I have here a good note here, which is section 9613. If AS provided is the amount of reinforcement is going to be larger than 1 1/3 of the AS required, which means required to resist the given moment, you don't really need to apply this AS minimum. Meaning if the demand is extremely small and you provided 4/3 of this demand as reinforcing, you don't really need to check the AS minimum, which is very good, right? In lots of cases. So what we have done in this example last time, we checked the AS minimum based on 3,000 psi concrete, 60,000 yield strength, 16 inch for the width, 27 inches for the effective depth. And with that, we needed 1.18 square inches of reinforcing intention. We did the second equation, 200 divided by 60,000 for F sub y. The width is 16 and the depth again is 27. Now I need 1.44. When I have two minimums, I'm going to take the larger of the two, which is 1.44. So the minimum needed by code is 1.44. Now how much is provided? I have two number 8. So each one of this number 8 has a cross-sectional area of 0.79 plus 1 number 9 of 1 square inch. So let me confirm this. This is going to be 2 number 8, right? And this one is going to be actually 1 number 9. Total provided 2.58 square inches. This is going to be more than 1.44. So we're good. We have no problem. We are able here to satisfy the required minimum reinforcement per code. So this beam passes this check. Now let's see what happened here in the last example in the slide set. This looks like to be exactly the same beam. Same concrete strength, same yield strength. It says, check the minimum flexure steel ratio provided that the design ultimate moment is equal to, just equal to one time, 125 kF/foot. So now I have the demand. So in this example, I'm trying to see if I'm going to be able to use this condition or not. All right? That's why they give me the demand. Demand is calculated out here, provided to you, 125 kF/foot. So now I know how much AS I have provided, and I have it solved already in the previous example. We said provided 2.58. Now the question is how much is needed to resist this demand. So I'm going to say the provided 251. I understand that. 258, excuse me. Now how much is needed? This could be the question. It's going to take me some time before I figure out how much is needed for this given demand. But what I can do, I can figure out PMN for this given reinforcement and beam section and concrete strength. Meaning, for this configuration, we have done already one example. And PMN is going to be equal to, look at this, 291 kip-foot. So instead here of comparing reinforcing to reinforcing, I should be able to apply the same concept and compare moment to moment. As if the moment capacity provided is going to be 291 and the demand is 125. Now, what's the ratio between the two? It's going to be 2 times 2.33 times. Meaning the capacity I have here is like 2.33 times the demand. This can be more than 4/3 or 1.33. So actually, I don't really need to check this AS minimum. If this makes sense, right? Someone else could have taken the 125 kip-foot and find out how much reinforcing is needed to resist this moment. But now it's going to be a longer problem, right? And once he found out how much AS is needed, he would compare it with the amount provided, which is this 2.58. If whatever here is provided is more than 4/3 of the needed, you don't really need to do this check on the minimum reinforcement. Any questions before I move to the next slide set?
Professor,
yes.
Can you go back to the moment slide?
Here?
Yes. Where is the value for 1.33? Oh, never mind.
This one here? This
no,
is
I got it.
the problem itself. It is 125 kip-foot.
Okay. I got it. Thank you, Professor.
No problem. Any other questions? I guess now I should move to the next slide set, which is about reinforced concrete slabs. We're going to call it here one-way slab. Here's a concrete slab, elevated slab. This is not slab and grade. This is not foundation. And when the slab aspect ratio, which means when you look from the top on a concrete slab, and you see here the length to the width of the slab is more than 2. You know that you have one-way slab. I want to give you here a quick example for one-way slab in the plan. Here's one case. Here's for a building. Just give me a second, please. Here's a reinforced concrete slab. And look at the length of one bay. So this is what we call here one bay of the slab from here to there. When you look at the bay length here, it's 26 feet. And the width is going to be 1/3 of this 28. So let's say about how many feet? Let's say 9 feet. When you take here 26 divided by 9, this is going to be more than 2. Let me explain to you what's happening here. What are you looking at? Here are columns, concrete columns, which is just shading. A column, 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 another column. This dashed line is going to be the drop beam. That's why we are showing it as dashed line. So we have beams running this way. So I'm going to call this is a beam. And this one here that I put the red line on actually is a girder, because a girder supports other beams. So this is going to be one beam, continuous, one beam, one beam, one beam. This is going to be a girder. Now, all of that, they support a thin concrete slab. Let's say 6-inch to 8-inch concrete slab. So actually this slab, if you like, is going to be performing in this way, because the load now would like to go from this side in the middle here. And from this side, it's going to be also coming this way. So for this specific panel, the load is going to be supported on this beam, on that beam. This is what you call here the load path. So load is going to be moving to this beam and that beam, meaning there is no direct load coming from the slab to this beam or to this beam, just simply because the aspect ratio of the slab, the width to length ratio. Also, nothing is coming to this beam here or to this girder. Load first goes to these two beams and then it goes back to the girder, because this girder here supports these two beams. So now the reinforcing, if you like to think about this slab, now this is going to be continuous slab, because here's the first span, second, third, fourth, just continuous. And the slab is the same throughout the entire width of the building. So if you'd like to design the slab, as I said once before, I'm going to be taking here a strip with a width of only 1 foot. And whatever applies to this foot strip is going to apply to the rest of the slab. So here's the strip. The width of it is going to be only 1 foot. So I'm going to put there, this is going to be 1 foot only. All right. So the width B, when it comes to analysis, I'm going to be using this to be 12 inches. So with the thickness, this is going to be whatever slab thickness that you'd like to serve. Let's say 8 inches. And the reinforcing is going to be at the bottom of the slab. It's going to be positive mode. Like what we have seen before in continuous beam, this is going to be the middle of the span. It's going to be positive. Above the support is going to be negative. Goes down to positive, negative, positive, negative moment. So the main reinforcing needed here is going to be right here in the middle of the span, is going to be at the bottom. So if I want here to put the bottom reinforcing, let's say I'm going to put it this way for you. And let's say here's the slab thickness, right? This give you the bottom reinforcing. And I'm going to have another reinforcing is going to be in the top of the slab like this. So actually I'm going to have 2 layers of reinforcing. One's going to be at the bottom, the other one's going to be in the top. Now this is going to be a pure rectangular section. There is no chance here for this concrete slab to be a T-section. This is the reason I can just use the same previous slide that we have discussed here and just use it in our analysis, in our design. Same width, but just in slabs, this width is going to be only 12 inches. The depth is going to be equal to the slab thickness, subtracting the concrete cover and 1/2 of the reinforcing diameter. Also, concrete is going to be failing at 0.03. We're going to start by this assumption that the steel is yielding till we prove otherwise. Neutral axis depth is going to be also called C. Same thing, A is going to be compression block depth. All the equations going to be the same. There is no difference between a beam and a slab in design except for the way that you put the reinforcement. I'm going to come here to it in a second from now. Also, the way that you cut out the reinforcing. How do you put the reinforcing program in the section? Same equations. Tension, compression, set them equal to each other. Once you set them equal to each other, you solve for A, compression block depth. And once you have that, you can check the phi factor to be sure it's going to be 0.9 according to the chart. And then after that, you find out the nominal moment capacity, which is equal to the tension or the compression multiplied by YCT, which is depth minus A over 2. We have done this before. We know what is this YCT. It's going to be the distance from here to there, right? D subtracting A over 2. Once you find out the phi factor, you say phi man is going to be equal to the phi factor. Hopefully, it's going to be 0.9 multiplied by n sub n. We have one example. It says here that you have here 10-inch thick one-way slab, simply supported over a span of 14 feet. So the span here is 14 feet. Slab thickness is 10 inches. Strength, 3,000 psi for the concrete. Yield strength, 60,000 psi. It says here the dead load includes, let's see here what does include. Self weight of what? Of the slab, of the 10-inch thick slab. And additional dead load of 7 psi. So this could be like ceiling, ducts, some mechanical equipment, maybe some light fixtures, whatever. And the live load is 50 pounds per square foot. Just take it as 50, right? It says here, check number 5 at 16-inch is sufficient. Yes, it says here number 5 at 16. What does it mean by that? It means that you are going to lay the reinforcing so that each bar is going to be away from the other one by 16 inches. It's going to be just continuous. This is not just 2-3 rebars. It's going to be just continuous, right? You're going to keep on adding rebars like this. So the spacing here says 16-inch. OC means on center. So let me put it here. Not just one time, not a couple of rebars. If you look back in the beam design, we just put 2 or 3 rebars because the width was limited, and this is the total number of rebars that we put in this concrete beam. But when you have concrete slab, it's going to be extended. So we're not just talking about 2 rebars, 3 rebars. We're going to have plenty of rebars. It's going to be running across the entire concrete slab. Like when you go here, it's going to be the rebars, right? We're going to put the first one here, right? Like this. It's going to be, of course, continuous. And you're not going to stop by just adding a couple of rebars. No, you're going to keep on adding. For each 16-inch spacing, you're going to be adding a rebar. And this is the difference between the two structural members, a beam and a slab. So it's a big issue. How would you figure out the amount of reinforcement that you added in this width? In concrete beams, for the given width, we're going to mention how many rebars you put here. So you can say, for example, 2 number 9 plus 1 number 8, or 2 number 8 plus 1 number 9, or maybe 3 number 8. We can just mention the amount of rebars here. In our case, when we have concrete slab, we're going to be considering the width to be only 12 inches. I'm not going to be taking it to be 16. As a challenge, how would you figure out the amount of reinforcing that you put in this strip of 12 inches wide? So first, let us look at the demand and how much reinforcing is needed. Demand here first is going to be dead load. Dead load is what? Self-weight of the beam plus 7 psi additional dead load. How do you figure out the weight of the slab? You take 10-inch, which is the thickness, divide this by 12 to put it in feet. Right? Multiply by 150. So what is this 150? I need your help. Where is this 150 coming from? Can someone help?
Weight of concrete?
Yeah, self-weight of concrete or unit weight of concrete. $150 what? Units pound per cubic foot, right? PCF. So if you take here 10 divided by 12, now you put it in feet because you need to be consistent when it comes to units, right? Multiply by 150, and then you add 7 PSF, the additional dead load for ceiling, ducts, piping, whatever you have in there. You have total of 132 PSF as a dead load. All right. How about the life load? You say life load is just 50 PSF. So now I guess it's clear to me how much is a dead load, how much is a life load. If you remember for the load combinations, we have two main equations that I need to consider. First one, it says ultimate load is going to be equal to 1.4 times dead load. Second equation says take 1.2 dead plus 1.6 life load. So, okay, good. Dead load is equal to 132. Multiply by 1.4, the load factor. This equals to 185. If you like, you can divide by 1,000, put it in kip per square foot instead of PSF. This gave you okay. So now I have 0.185 kip per square foot as dead load. Multiply by 1.4. The second load combination equation says 1.2 dead plus 1.6 live. And let's try that. Let's take the 132, multiply by the load factor of 1.2. Let's take the 50. There's no change here in the 50, right? Just as given. Multiply by 1.6 and add them to each other. I have here 238 pounds per square foot. Now, out of these two load combinations, I'm going to say this value here is going to be controlling my design. This is what I need to consider when I design the slab, not this one. So the way it works with this load combinations, you try both of these two load combinations and you pick the one that controls, which means the one's going to be yielding higher value of ultimate load to you. Okay, now this is going to be our design load. Is it okay?
So I have a question.
Yeah, that's good.
When we're doing the LRFD ultimate loads, do you want us to try both the 1.4 dead and the 1.2 dead, 1.6 live to see which one is higher?
Yes, absolutely. And
okay.
let me just...
Even if we have live loads, we still try the 1.4 dead?
Yeah, because sometimes it controls. It depends on the ratio of the dead load to the live load.
Okay.
If the live load is so small compared to the dead load, the first equation is going to control your design. Let me mention something here to you. You said LRFD, okay? So usually the term LRFD is used in design of the following: steel, wood, masonry, right? How about for concrete? What do you call it? Do you still call it LRFD?
I know we usually use ASD.
For what?
Whenever, in my work, whenever we have concrete anchors or concrete design of any sort, we usually use ASD.
Now, according to the code, and if you run one of the software like Hilti, for example, or Simpson, there is also another one for Simpson, it all runs for the LRFD now, for the strength. And I don't want to use LRFD because the term LRFD is usually used for steel, wood, and CMU. Okay? But when it comes to concrete, usually we call it strength design. Let me show this here for quick. Looks like it's not in this slide. Maybe in slide set number 3. Let me get that. This term here is mainly used for steel. Structural steel, you can do ASD or LRFD. In concrete, you use either ASD or strength design. So usually when it comes to concrete, we don't use the term LRFD. So we use the term strength design, which is the same as LRFD, same concept. Everything is exactly the same, but just the common way of calling it. When you open the ACI, you don't see, for example, LRFD, you see strength. This is why whoever has written this code, the CBC and the IBC, decide to put two terms next to each other. So concrete people are happy and steel people are also happy. No one's gonna say, no, this is not ours. So he's telling him this gonna be for LRFD, which is the same as the strength design. All right. To confirm my answer here about your question, it is true, yes, that you're gonna try both of these two load combinations and then you take the larger of the two. I want to hear for a second if you say, if I put here the live load to be only 10 PSF, which load combination do you think is gonna be controlling your design? So I'm gonna put here dead load 132, just hypothetical here. You can see here, dead load 132. Live load 10 PSF. Can someone help me here? How much is 1.4 times dead? So you can just read it there. It's gonna be 185. How about 1.2 dead plus 1.6 live? I need your help. How much is that?
It's 174.4.
174? Okay. PSF. Now you see which now one controls? So the amount of live load is going to be very small. Your dead load combination is going to be controlling your design. So just one example here on the side. Does not really about our example here for the concrete slab design, but it is good that you understand why do we need to try both of these two load combinations. All right. You say, okay, here's the load, design load. I need the design moment. How much my moment demand on the beam? How much moment you want your beam to support in terms of ultimate factored load, factored moment. All right. Here's the moment equation. It's simply supported, as it says here, simply supported. The span is 14 feet. So we can say W, the 0.238 times 14 squared, L squared divided by 8. It's going to be 5.83 kF foot. So you wanted your slab here to support 5.83 kF foot. And you know the amount of reinforcing provided says number 5 at 16. So, okay, good. Here's number 5 at 16. So great. Now, how much is the moment capacity for this concrete slab? And when you look here at this moment demand, is this for 1 foot strip? Think about it. This unit here, if you look at the units for loads, it used to be here KSF, K per square foot. We have taken it, multiplied twice by the span, WL squared. So when you have K per square foot, applied by square foot, it's gonna be only in kips, correct? You guys follow me? So in terms of units, when you look at this moment, it's gonna be as in terms of kip. Does make sense. Because when you have here kip per square foot, you'd like first to put it as kip per linear foot. Let me write this down. The load that you'd like to use here for beams is gonna be the load W. It has to be as in kip per foot, correct? It is not really kip per square foot. So what happened? Simply that I said, well, the strip width here is gonna be exactly 1 foot. Meaning this W ultimate that you just calculated out is equal to 0.238 kip per square foot. I'm gonna say multiply this by 1 foot for the strip width. Okay, it's gonna be equal to what? It's gonna be equal to 0.238 kip per linear foot. That's what I've done. So actually this moment here is calculated out for what? It's calculated for 1 foot wide strip. So now I understand that the width B, this is what I have used to be exactly 1 foot or 12 inches. Now let's look here at the reinforcing. The reinforcing, you have number 5 at 16 inch, meaning the spacing from one rebar to the other one is 16 inch. And your width is only 12 inches. So a person here would like to give you this example and says, on average, when you have here this at 16 inch, how many square inches you have of the steel reinforcing per 1 inch wide strip? If you'd like here to divide into pieces, very little pieces next to each other. How much reinforcing as square inch you have it per 1 inch? Only per 1 inch. You say, well, the number 5 meaning what? 0.31. If you take this 0.31 divided by 16, it's going to get you what? So let me write it here. You can say the following. AB for just one rebar of number 5 is going to be 0.31 square inches. And I have this at 16 inch. The spacing is going to be 16 inch. So at each 16 inch, you're going to see one rebar, right? So I'm going to say AS per an inch, right? For each inch, it's going to be equal to how much? It's going to be 0.31 divided by 16. Does it make sense? Can someone help me with this value? Yes? I don't want to do it this way, but yeah, go ahead, guys.
.019.
Okay, good. Square inches per what? Per inch. Does it make sense? Are you guys following me why it is going to be per inch? Because I have this 0.31 square inches repeated at each 16 inch. So I'm trying, there's a term here that I use from a guy who's really working structural steel, and every day he's just using weld and stuff like this. So he's used to do lots of welding. So he says, it seems to me that you're melting it. You're taking this rebar, you're heating it up, and you're creating a very thin layer, right? Of steel. Does this make sense? He says, it seems that you're putting the fire to it and you're just melting it. You're creating a very thin layer. And you're asking us for each inch, how many square inches are we going to be cutting through? So yeah, it's going to be 0.019 inches square per inch. Now the real question is, how many square inches do we have in the 1 foot strip? I'm going to say, okay, for 12 inches, what do we have? I'm going to say AS equals 0.019 times 12. How much is that? Can someone help?
0.228.
Yeah, 233, which is this one here. This is exactly what I'm doing. If you look here at this equation. For 12-inch slab strip width, what do we have? I'm going to have here AS to be 0.31 divided by 16 inch to find how much per inch, and then multiply by 12 to find how much do I have as an inch per square foot. So units here is going to be inches square per foot. This is actually the main difference between beams and slabs when it comes to the amount of reinforcing. How do we calculate that? Questions? Any questions? No?
Yeah, I have a question.
Yeah.
So when we calculated for MU, L is to the second power. How is it that we have an extra feet?
Okay, here.
Yeah, because it's pound per square foot times foot squared. That should cancel out.
Now, it is not going to be pound per square foot. It's going to be actually pound per foot, per foot. This is what I'm trying to say. Yeah, because
that's what you were saying earlier.
By 1 foot, right?
I see. Okay. So there's actually 1 foot in the formula.
Equation, but usually we don't consider it. We just do it without talking about it.
Okay. Thank you.
Yeah, very good question. Thank you. I said, okay. So here's the amount of reinforcement that I have. It's going to be 0.233 square inches per foot, right? And this is what I need to use in my analysis to find out the moment capacity of this beam. Actually, a slab. It acts like a beam. So now here's the depth. Depth is going to be what? 10 inch for the total slab thickness. Subtract 1 inch cover and 1/4 of an inch for 1/2 of the bar diameter. So we're going to say this here accounts for what? This 1 1/4 cover plus 1/2 of bar diameter. So I'm going to say here 8.75 inches. This is going to be the effective depth. Now you want to figure out how much is this A, compression block depth. We said tension equals to compression. 1398, this is going to be AS. What is that? What's the 1398? This is actually AS times 60 KSI to give you the tension. 0.85, constant. 3 KSI for F prime C, and the width is going to be 12 inches. So be sure that you understand where is this coming from. This 12 inches is going to be your width B for the strip. See how much is this? 0.46 inch. Now, before I go through this fee determination, right? Think about a depth of 875 and compression block depth of like 1/2 inch. Where do you think your fee factor is going to be? Let's say fee factor is going to be so high because look at the ratio. You remember the ratio of the depth to C, neutral axis depth? We said if C is going to be equal, let's say about 1/2 of D, the strain in the steel is going to be 0.03, correct? Now this C here, or A, is actually extremely small compared to the depth. I'm expecting high strains here, and look at this. Here is the C value, like 0.54 inch. C over D is very small, therefore your fee factor is going to be 0.5. Great. Look at this. You're all the way here. Because look at this. C over D is 0.06. This here is going to be 0.375. 0.06 is going to be all the way to the right, meaning the strain is going to be so high. Your fee factor here is 0.9. This is good. This is very good. Now let's find out here Mn and phi Mn. Here is Mn, nominal capacity. I'm going to be taking the tension multiplied by, or AS multiplied by Fy, 13.98. 875 is going to be the effective depth. And here is A compression block depth divided by 2. Now the answer here is going to be in kip inch. Why? Because all of this is going to be in inches, right? This YCT is going to be in inch, and this is going to be in kip inch. Don't forget here to divide by 12 to put it in kip foot. So how do you get from here to there? You divide here by 12. It's great. You have a fee factor of 0.9. So here's your capacity, 893. How much was your demand? Given here, 583. So this beam is okay. Or this slab section is okay with number 5 and 16. Are we good? Questions? No questions? All right. So when it comes to beams, for the minimum reinforcement, we have 2 equations. Just to remind you, what equations? If you remember the four beams, minimum reinforcement, getting to it is right here. And we said that this is going to be only for beams. I say, how about for slabs? How do you find out the minimum reinforcement for slabs? Do you use the same two equations? I can say no. For slabs, I'm going to be using this equation here, also from the code. Concrete slabs, minimum reinforcement is going to be equal to 0.0018 concrete cross-sectional area. This concrete cross-sectional area would include the total slab thickness, not the effective depth. So look here at the equation. Slab thickness, 10 inches. The width for the strip is going to be only 12 inches. AS minimum, 0.0018 times 10 inch for the thickness, not the effective depth, times 12 inches for the width. So this square inch is going to be per foot. Why? Because I consider the strip of 1 foot. How much did you provide? If you remember this equation, what we have provided is 0.233. So this is good. It's more than 0.216. So we covered this slab when it comes to minimum reinforcement. Just so you know, this equation here, it works for slab and foundation. It's right there. It works for slabs and foundation, for both of them, not just for slabs. This gave you for slabs and foundation. You provide minimum of 0.0018 times the concrete cross-sectional area. Any questions? We're good? 100%? You have a question? Do you have any question? All right. Should I move to next slide set? Yes? You guys think that old slab design is covered 100% or not really? You guys have this slide set online? You should. Do you have it on Canvas? Number 6? Yes? No?
Yes.
Okay, very good. All right. So in the title here, it says T beams. Now we're done here with the rectangular beams and the slabs because they're all like rectangular section. And doubly reinforcing beams. What's this doubly reinforcing beams? This means that I used to put the reinforcing only at the bottom when it comes to tension. I'm gonna put reinforcing bars in tension and compression. As you see here, beams usually is like gonna be T section. We said, well, if neutral axis is gonna be happening within the flange itself, it's gonna be rectangular. So this section here, or the slide set, is gonna be covering the cases when neutral axis is gonna be falling below the concrete slab. Here is the slab, supported on beams, same picture I showed you, very similar to this picture. You guys recall this, just direction is different. But look at the aspect ratio for this slab. 32 divided by 15, this is gonna be more than 2. That's why we're gonna call this one-way slab. Load is gonna be moving this way. Same thing here, 3 divided by 12.5, more than 2. Load is gonna be going the short direction. Short direction, same thing. 32 by 10 is giving the short direction. We call this a beam that supports the slab directly. And the girder is gonna be the structure member. It's like a beam, but supports beams. So here's the section throughout the beams and the slabs. And as you see here, this slab is really continuous. It is spanning on the top of the beams, and the beam works as a support to the slab. I understand that. The big question is, how much is the effective flange width that you need to consider? If the slab is extended on both sides of the beam, now you understand that this slab is going to be helping in compression. So someone's going to say, I can simplify this case and just put my beam to be like this. They say, okay, this is okay. But in many cases, if you add a little bit of the concrete slab to the beam, you're going to be saving maybe a couple of rebars. So why don't you use it? If you have a chance to use this concrete slab to enhance the strength of the beam, go ahead and use it. When it comes to equations, it's going to be the same equations. We don't have any new equations. As long as we work with beams, slabs, footings, it's going to be the same equation. It just depends on the way that we use it. When it comes to columns, yes, go ahead.
Going back to the last slide, it says this is a T-beam. How is this different from the beam on top of the girder that we learned in the one-way slide?
Let's say here, right?
Yes.
The section that here you are looking at, right? Look at this. You have one beam, another beam, a third beam, right? Is the section cut this way? And looking this way, right? Okay.
Yes.
So you have one beam, here's the second, the third, and then the slab spans like that. So when you cut the section, it's going to be something like this. You're not going to see this line when you cut the actual section concrete, right? So you know that you have this slab is going to help you in compression. And you understand that when it comes to performance of the beam is not going to say, oh, the slab is not doing anything to me. I can just take care of supporting the load. Part of this slab is going to be helping the beam to resist the load. So I understand in reality, this is going to be like a T-beam, like the way that you see it here, right? And the question that I don't have an answer for at this point, how much width of the concrete slab would you consider when it comes to the beam design? For example, if the distance from here to there, let me draw a line. Let's say distance from here to there, which is called here beam spacing. See this beam spacing? Let's say this distance here is 10 feet. Okay? From here to there. Someone can come here and say, you know what? Let's go here to half the way, and half the way from the other side, if the spacing is consistent, to be also 10 feet. So therefore, the distance from here to there is going to be how much? It's going to be 5, and from here to there is going to be 5, right? So the distance from this point to this point, all the way to this point is going to be how much? You can say it's going to be 10 feet. Means the effective flange width here is going to be equal to the whole thing is going to be 10 feet. And this is going to be your T section. If you like, I can just do it like this. Correct? Can do your T section like this. Right? So I'm going to say this is going to be our section here with the width of 10 feet. Someone's going to say, but this is too much. I mean, you cannot really take the entire, I'm going to say your natural boundaries of the T section. Why? Because you assume that one half of the slab on this side is going to be working with you, the other half is going to be working with this beam. You see, this is too much. Why? Because you say there's another factor that contributes to this issue, which is the beam span. We're going to be taken also as a ratio of the beam span. All right? You take here a ratio of the beam span and compare it to this natural boundaries of the T-beam, and then pick the smaller of the two. This gives you the right answer. All what I'm trying to say here, code has a say when it comes to the effective flange width. You cannot just take any value. There's certain guidelines that we're going to be going through. Okay? We're good? Okay, good, great. When it comes to the design equations and analysis equations, can be the same, nothing new. Difference is that in here, we're gonna have here tension is gonna be at the bottom, and on the top compression, you're gonna have a flange. And the concrete section is gonna be all of that. So we're gonna have here larger compression area when it comes to concrete, which is gonna help us out. About equations for analysis? Same, no change. The same ones that we have used for the rectangular section. Now here's our T section. And let's start with an example. Since there's nothing new, right? Let's just do an example. In this example here, they give you the concrete strength, yield strength, section properties. They say effective width of the beam is going to be 32 inch. It is predefined to you. Depth is 12. You have 3 number 9 with AS of 3 square inches. The width of the web is going to be 10 inches. And look at this. They say the spacing of the beam. You see this? You have a beam at 32 inch on center, which means I'm going to have another beam very similar to this. It's going to be at 32 inch on center. This is why the effective width here was taken at 32 inch on center. If this makes sense to you. Just because it's really close to each other, the beams are really close. I mean, when the beam is at 32 inch on center, it means that they are closely spaced. We're not talking here about 10 feet or 20 feet, like in typical and standard beams that we see and slabs. So I guess here, just 32 inches, very close. Most likely this is what's controlling the width of the slab. As we understand, tension is going to be at the bottom, at the 3 number 9, compression is going to be in the top. We don't know here the exact compression block depth. So if we run the analysis for the beam, and we find out neutral axis and compression block depth is going to be more than the slab thickness, I'm going to call this the T section. Let me look. So at the beginning, let's just consider that this rectangular section and the compression block is going to be right here. It's just my assumption, right? Because it could happen. If A, the compression block depth is going to be within HF, you know what's going to happen in this case? I'm going to consider it to be a rectangular section, right? Now, where is the width of this rectangular section? It's going to be the 32 inch, not the 10 inches. As if my entire section looked like this. It's my first assumption. So I said, okay, let me check this first. I'm going to consider the width to be 32 inches. Depth is 12, AS is 3 square inches. A compression block depth based on static tension equals to compression. Look at this value here, 2.2 inches. It is going to be right here. This is wrong. Why? Because this cross-sectional area, the actual one, is not really equal to 32 by 2.2. This equation here implies, you see this equation, implies that I'm gonna have a compression area of 2.2 multiplied by 32. Let me show you this equation here. I'm gonna type the same equation again, but just gonna do here a small trick. If this is true that the exposed area to compression is 2.2 times 32 inches, how much is this? I'm gonna call this area of the concrete. I need your help, guys. How many square inches? How many?
$70.4.
70.4, very good. Square inches, good. So this equation here, if you just ignore this T thing for a second and say, well, this equation, when we use it for rectangular section, it means this is gonna be the cross-section area exposed to compression in concrete, right? This means the compression force equals 70.4 times 0.85 times how many KSI? You can see 3 KSI. How much is that in terms of the force kips? Yes, Adrian, do you know the answer to this? Adrian, are you there?
Yeah, I am. I'll
Yeah.
put in the calculator.
Help me, my friend.
I got 179.52.
5, something like that. Okay, good. This is going to be the compression, provided that the cross-section area exposed to compression is 70.4 square inches. How about the tension in the steel? I'm going to say tension in the steel is going to be equal to AS. How much is AS? Can someone help with that? Brandon, how much is the square inches? Like cross-section area of the steel? Brandon, yeah?
3 inches square.
3 inches, yes, this is correct. Times F sub Y of Cindy, how much is F sub Y?
60.
60. Okay, very good. So I have here 180 kips. It does make sense because tension needs to be equal to compression. But based on this assumption that the cross-section area is going to be 70.4, tension is not equal to compression. So I did something wrong. This 2.2 is incorrect because I don't really have all of this area exposed to compression. So when I say here 2.2 total depth of this red box times 32 inches, I was overestimating the compression force or underestimating it. You can say I was overestimating it. Why? Because look at this area here. It's empty. Look at this area here. It's empty. There is no compression on this side. We don't have it. You just do the math here. So I'm going to see here I have 32 times 2.2 times 0.85 times 3. Yeah. I don't have that. So this is why I have a T section. And in reality, actually, I'm going to have 2 compression forces. I'm going to have 1 compression force for this section and another compression force for this section. Why would I have 2 compression forces? Someone's going to say, why don't you just do it as 1 compression force? You say, yeah, this is going to be good. But you know what's important? It's not just to figure out the amount of compression force. It's going to be also centroid, the point of application of this compression force, resultant force. If you have here 1 big force to be called C, the big question is how much is Z for it? But when I have here 2 compression forces, I can come up with Z1 and Z2. Very similar to the uncracked concrete section that we have used. If you recall this design here that we have done, if I may just take you back there and say, okay, here's a slide set that we were talking about. And then you said that you are going to have more than 1 Z, right? What's the reason for that? Because it was really tough to find out 1 resultant force for all of these compression components. So I said here, I'm going to do something very similar to it. I'm going to divide the compression force into 2 forces. So I said, okay. I'm going to say compression force number 1, I'm going to call it C sub F because it goes to the flange. The other one is going to be compression force in the web. So the first one goes here with this A1. And the second force here, compression in the web, it goes here from the second cross-section area. The good thing about this analysis, that the stress is uniform on the top of it. Meaning this compression force is going to be equal to A1, 2 inches times 32 times 0.85 F prime C. If you remember here in crack section, that was kind of tough, right? That was not an easy task. You guys remember that? Let me put it back. Look at this. It's not an easy job to find out this force, if you remember. One of them was equal to this rectangular force, right? And this one's gonna be this triangular stress distribution, and this one's gonna be triangular stress distribution. I don't have any of that. My analysis is gonna be much easier because I have uniform stress of 0.85 throughout the entire area. How about the tension force? I'm gonna say tension force is gonna be the same. There's no change here in the tension force. It's gonna be equal to AS times Fy, but you know what? This tension force is gonna be equal to Cf plus C sub W. It's gonna be equal to summation of the two forces as a compression. So should I consider this to be the piece here below the slab? Let me go here in the top. If you consider this to be 2.2, like in our analysis, it means this little piece of the web is going to be equal to 0.2 of an inch. And if I do the exact area here, so I'm going to try another analysis here. I'd like to do here some analysis. I'm going to say the area of concrete, according to this, is going to be equal to 2 times 32 plus. What's 2 times 32? Slab thickness times the width. We're going to say plus 0.2 times 10 inch. How much is that? Is this correct? About right? Yes? You have 64 plus 2 is going to be 66 square inches. I said, okay, good. It's provided that I had taken the exact cross-section area like this. Okay, good. Let me take the compression force to be equal to the 66 times 0.85 times 3 KSI. Very similar to what I have done here at the bottom. How many kips are we talking about?
$168.3.
All right. 168.3 kips. Something's wrong. This is not 0.2 of an inch. Actually, I have here two areas. It's going to be area 1 and area 2. Area 1 is fixed number. It's going to be 32 times 2. It's going to be the 64 inches. Area 2 actually is going to include my variable A. You see this variable A? So this determination of A is wrong. Meaning once you find out your neutral axis coming below the concrete slab, you know that your analysis is wrong and you need to redo it. How do you redo it? Okay, look at this. Here is A1. It's going to be 64 square inches. Fixed number, you cannot change it. But A2 is going to be equal to this little depth. Now, this is going to be our new variable. I'm going to call it A sub 2 times the width 10 inches. So it's going to be equal to 10 times A2. If you take 0.85 F prime C, multiply by the entire area exposed to compression, you set it equals to AS times Fy, you will get the correct answer for A sub 2. Show you how this is done. Here's the first force in the compression block on the top. Here's the second force in the web. I guess I'm gonna stop at this point. I don't think that I'm gonna have enough time to finish this example. So I'm gonna stop right here and then we'll continue next time from where we stopped. Any questions before you go?
Just a quick question.
Yes, go ahead.
So because our analysis initially was incorrect, we have to do this whole thing again. So we can't use that 2.2 anymore.
Yes, this is correct.
Okay.
I proved it. I tried here to prove it. I said, well, let me try this here. No, it doesn't work. Let me try this here. It doesn't work. Right? Very good. All right. See you next time. It's Gabe in class.
Thanks, Professor.
All right. Thank you. Have a good night.